Alright, hello. Everything seems to be working, so we are going to be recording an explanation for homework number 10. I have some music going. This is what it's called if you want it. We're going to be using Excel. Okay, this is going to take a wee bit of time, but that's alright. So what we're going to start by doing is just explaining a few things that you need to know before you do this, and then we will... then we're going to explain every single question. So first, we are going to go over PV equals nRT, just really basically, and we're going to go over the density equation, and then we're going to go over some other things, and then we're going to start. First, PV equals nRT. So one of the most important things that we have to know is what are the units. You have pressure, volume, moles, R, and T. P, pressure, is in atmospheres. Atmospheres are equal to 760 torr. Doesn't like that. I know. I don't care. Oh my lord. There we go. Atmospheres, one atmosphere is equal to 760 torr. Some people didn't seem to know this, so I'm just gonna... When we do PV equals nRT, P is going to be in atmospheres. So if you have it in torr, you need to convert it. If you have it in torr, divide it by 760, and you'll get the correct number of atmospheres. You shouldn't need to turn atmospheres into torr, but if you do, just multiply it by 760. Volume is in liters. 1 liter... Ooh, that didn't do what I wanted to do. 1 liter is equal to 1,000 milliliters. So if you get something in milliliters, divide it by 1,000. Now, if there's like 1,000 or more of it, just put the dot here. That is now 1 liter. It's not too hard, but it is important that everything is in the right units, or this equation does not work. N is in moles. That's not too hard. It's not molar mass. It's not grams. It's moles. That's pretty simple, I hope. How many moles is going to per gram? How many moles per gram is going to depend on the molar mass of the substance, and so on and so forth. R, excuse me, is just simply, while we're doing this homework, it's going to be this. There is another number for it, but that's when we're using joules. Right now, though, we don't have any joules. We have atmospheres, liters, moles, and Kelvin or Celsius. Kelvin, specifically, not joules. So the R uses... let me get my book, because it is pretty long, and I don't actually have it perfectly memorized. It's not super important that you have this memorized, but it's just important to know that this does have units, and there is a reason for that. So this unit is, if we can find it, here we go. It's in liter times atmosphere divided by Kelvin times mole. So basically what this means is that when you plug all of... Okay, let's go ahead and go Kelvin, and then I'll finish explaining that. So temperature is in Kelvin. So for 0 degrees Celsius, we have 273 Kelvin. So that's 0 degrees Celsius. I don't know how to do the degree symbol, so you just have to believe it's in degrees. So the way you convert from Kelvin, Celsius to Kelvin is we have 0 degrees Celsius, you add 273. If we have 30 degrees Celsius, that's going to give us 303 Kelvin. You just add 273 to whatever your Celsius number is. It's pretty simple. It's not too hard. You should be able to figure that one out. Now, the reason this is important that you have this in this units is that this equation works because this R value is based off of ideal gas law at STP. And everything else is just movement along these directly and indirectly proportional lines, more or less. So if it's not in liters, it's not in atmospheres, it's not in Kelvin and moles, this equation doesn't work. So you have to make sure that your units are proper and correct before you do anything. Next, so I'll just leave it there for a second so you can get that. Okay. Next, we will go over density. So this is something she taught Tuesday last week, at the very end of the lecture. So if you like left earlier or whatever, you might not have gotten it. But it's pretty simple. It's just density equals, and it is density equals pressure times the molar mass, and we're gonna use M, capital M for molar mass, over RT. So what this is I'll just put down the units to explain it. It's grams per liter. So density is grams per liter. It's how heavy something is per every liter of gas. So if you have 10 liters of gas, and you dry it, and you get 10 grams of whatever substance it is, your density is 1 gram per liter. Maybe this is here. Let me use a slightly better example. If you have 15 liters of gas, and you have 20 grams. We can go ahead and get rid of this. What you're going to do is you're going to divide the grams by the liters. So we're going to do 20 over 15. Grams over liters. And we're going to get 1.33 grams per liter. That's our density. That's how we get it. We divide number of grams by the number of liters. It's important that these are the same substance. If they're not the same substance, it doesn't work. The grams, it doesn't really matter what the temperature, pressure of the grams is because it's solid now. And it doesn't matter what the liter, it does matter for this equation, but just for finding the density, it does not matter of what are the atmospheres or whatever. That's part of what makes it useful, is that it doesn't need to convert to moles, especially if you don't know the molar mass, etc., etc. Sometimes this is what we have to use. So it's in grams per liters, and, converting this from moles, usually you're finding the density and then using it to find moles. So, conversions of this are difficult. Try and figure it out, I guess. P is just pressure. It's just in atmospheres. I already went over that one. M is molar mass. So usually when you're using this equation, you want to find a molar mass and you have a density. Molar mass is just however much the molecule weighs. So H2O, for example, is the 2 hydrogens, which is 2.02, plus the oxygen, which is 16, and we get 18.02 about grams per every mole. And that's what this is in. It's grams per mole. And then the next one, we have R and T. We already went over this. R is just 0.082, and we have, and it's in, whatchamacallit, where is it? It is in, over here. Liters times atmospheres divided by K per mole. So I'll show, so this equation, we actually, if you watch the lecture, which you can do if you go to lectures online, it is this one, I believe. Here, we can go ahead and just, yeah. Yeah, I think it's about, no, I'm wrong, I think. Maybe it was, yeah, I think it was this one, actually. Yeah, here. Here, she, I believe it's here. Maybe it's a little bit further. Ah, here we go. Ooh.
So can I show the mass? Don't I have my mass over RT equals...
So right here, so it is in, it's this one. If you go here, you watch this one. Here at the end, it is at the very end. So you might not have caught it, but she explains how to how to get the density formula from PV equals Nrt. I'm not going to go all the way in and explain exactly how to get it. I just want to explain how to use it. because that's what we care about today. So this, and then we can just find T, and it's just in Kelvin. It's just 273 Kelvin per 0 degrees Celsius. So what happens is, if you have our grams per liter, so we can move this down, grams per liter is equal to grams per mole times our pressure in atmospheres divided by this, which is long, so we're going to copy it, times, and then we can move this out a little bit because we are running out of space, Kelvin. Now, as we can see, we can go ahead, so this is on the bottom. If there's a line here, that's division. Just imagine. I'm sure I don't know how to do it. But simply put, we can show that this works by crossing out stuff. So grams, so this is an equal sign right here. Just put it here. There you go, there's an equal sign. So we can cross out stuff to show that it works. Grams, grams, and then we can see this divide by mole, this crosses out. This crosses out. We have this liter, this over liter, and over liter. These cross out. But basically what we're doing is we're multiplying both sides by the liter. That crosses out. Then we have atmospheres on top, divided by atmospheres. We can get cross that out. And then divided by K, and divided by K on the same side. You can cross those out as well. If you don't understand how that works, don't worry about it. It's not too hard. It's hard to explain. It's basically just algebra. But if you don't understand it and you don't want to, it's fine. You don't need to. I'm just explaining it for those who want to better understand it without watching the lecture notes, which you don't have to. You can just watch this and not perfectly understand it, and that's fine. For the sake of this homework, probably don't need to perfectly understand it. Okay, so we can leave this here for a moment, so you can get it if you want to. And then we're going to get rid of that. And now we can start, well, one last thing. At STP, she explained this in class yet again, but I want to reiterate that at STP, 1 mole of any substance, not really, which we went over in class today, but to some degree, but we're ideally, and in this homework, 1 mole of any substance is equal to 22.4 liters of gas. So this is very important for this homework and will save us a lot of time. So at STP, and I almost forgot. STP stands for Standard Temperature and Pressure. That temperature is 0 degrees Celsius, or 273 Kelvin, and the pressure is 1 atmosphere, or 764, which is the same as 1 atmosphere. So I'll leave that there for a minute, real quick, and if you want to get that down, pause it, and then, okay. And now we can start on number 1. Now, for number 1, I want to go ahead and put PV equals Nrt back up here, just real quick. And then let's look at number 1. So number 1, if the volume of a sample of gas is increased 5 times, so this is the V, increased by 5 times, right? So we can just say, in parentheses, x5. Multiply that by 5. While the temperature is held constant, so the T does not change. This is constant. What happens to the pressure of the gas? Now, because it doesn't mention that we're gaining or losing, the N is also constant. Generally, you're going to assume that the N is held constant unless they tell you otherwise, because that would make this too complicated and this wouldn't be that sort of problem. So, if this is going up by 5 and nothing else is changing, what else has to change? The volume goes up by 5, so because it's on the same side, it's inversely proportional. So the P is now going to go down by 5, so it's going to be divided by 5. And as we can see, these two cross out and the equation does not change, but P and V each themselves change. So the pressure decreases by 1/5. As you can see, that's the right answer. And next we go on to number 2. Okay, so I don't think we need this for this one. We will need it for number 4. So we're just going to leave this here. These parentheses. Okay, number 2. Suppose you inhaled 1 liter of air at 30 degrees Celsius and held this air long enough to heat it to body temperature at 37 degrees Celsius. What would be the new volume of air in the lungs, assuming the pressure remained constant? Okay, so So what's happening here is we have pressure not changing. Pressure is not changed at all. In is not going to change at all because you're holding, it's the same air. You hold in your lungs. So we have X volume of air, which is going to be in volume of air. The V can change, but unless we introduce new material, the in cannot change. So the in is also the same. So the pressure is constant, and the in is constant. The temperature, however, T, goes from -30, which if we convert it to Kelvin really quickly, 273 minus 30 is 243 Kelvin. And it becomes, oh, don't do that. That's annoying. Oh my gosh, I know, it's terrible. Oh, shush you. No, it's dash. Oh, I do not like Excel sometimes. Fine, I won't use the arrow symbol. We're just gonna, can I just use the arrow symbol? Like, can I just do that? Thank you. There we go. Okay, anyway, like I was saying, 243 Kelvin goes to 37 Kelvin. 273 plus 37 is 310 Kelvin. 310 Kelvin. Doesn't matter what case it is. So, T, and we're looking for volume. So the volume is changing. 1 liter, the V is 1 liter, and will become what? So because they're on opposite sides, V and T are directly proportional. Whatever multiplier we use to T has to, because P and V in are constant, V has to change by that same multiplier, right? So what are we multiplying by 243 to get 310? We can go ahead and right here, equals 243 over 310. And we can see that 243 is about 78% of that. I actually did it backwards if I want to find the multiplier. I want to find a multiplier that I can multiply it by. Okay, there we go. So if we multiply 1 by 1.275, whatever, 1.275, we will get our new volume. Because this is only 1, that's pretty easy. We can just plug it in, 1.2, and let's say 8, round that up. So that wasn't too hard. We just found out what this multiplied by to get its new number, and we did the exact same thing in here in order to balance our equation. So as we can see, it was number 4, and number 4 is correct. And now we can go to number 3, get rid of this. A sample of gas at 200 degrees Celsius has a volume of 5 liters. The volume expands 10 liters due to a temperature change at constant pressure. This is the exact same problem. In fact, we can go ahead and do this, and we can just get rid of these numbers, because it's almost the exact same problem. The only difference is which one of these is changing. In this one, the volume, or what we're given rather, the same things is changing. So the volume is 5 liters, and changes to 10 liters. So in this one, it's pretty easy to tell. And wait, we want to go ahead and do this number. So 200 plus 273 is 473, right? Kelvin. So it's pretty easy to tell that our volume is multiplied by 2. In order to find the new temperature, all we have to do is multiply the absolute temperature in Kelvin by 2. Remember, we want to make sure that we're using Kelvin. So what is 473 times 2? And we get 946. So our answer is 946 Kelvin, but this is in degrees Celsius. So we have to then put this here and this here, and then we are going to take away 273 to find our Kelvin. If you want to find, or sorry, Celsius. If you want to find a Celsius number from Kelvin, just take away 273. So we get 673 Celsius, which is number 2, which is correct. Number 4 says, if a sample of gas is heated from 100 degrees Celsius to 300 degrees Celsius, so this is temperature, the volume will, okay, so we're doing temperature and pressure. I believe that's correct. Yes, temperature and pressure. So we just have to replace this with P, sorry. We can just delete. Okay, so we have temperature 100 degrees Celsius. We can go ahead and convert this. It's pretty easy. It's just adding 273. So it's 373 Kelvin, space and it increases by 200 degrees, so that's 573 Kelvin. Okay, so it's asking the volume will x by a factor of x. So because these are, just like with v and t, p and t are also on opposite sides of the table on the equation. And so when one increases or decreases by a factor and these are kept constant, so as you can see, constant pressure, and it doesn't, and when it doesn't talk about, it almost never talks about the moles changing. If it does, which I don't think we have any moles changing like this in this one, but if it does, then we'll just do the same thing. But we can assume the n isn't changing because it doesn't mention it, right? So there's no more instruction, it's just this. So all we have to do is, well, for one, this is increasing, right? T is increasing, and in order to balance the equation, because V isn't increasing and N isn't decreasing, P has to increase. So firstly, this is increasing, right? So this is going to be increased. There's only two, about 3, about 1.5. Now, why would it say by 3? Well, look, it increases by 3, right? 3 times 100 is 300. But it is not directly proportional in Celsius. It is only directly proportional in Kelvin. So actually, 3 is completely wrong. And we could go ahead and know that it's 3. And I've already done it, so it's, it's 3. But if you want to do the math, we can go ahead and do 373 divided by 573. And we can see, well, I keep doing it wrong. Like, if you do it the other way around, then it'll give you... See, what that gives me is how much of this, the percentage, so this is about 67% of this, which is not what we're looking for. We want to see if we multiply this, what do we multiply by to get this? So it's actually going to be 373. No, I'm doing it again, wrong again. God. 373. There we go. There we go. Okay, so that's our number. It's about 1.5. Yeah, about 1.5. So that's the right answer. Just kind of make sure you've got the right numbers in the right place, or you'll mess up. Anyway, we can go on to number 5. That one's not too hard. Just make sure you're doing, like I said, the units are very important. If you think about it in Celsius, because they are proportional in Celsius, it does go up, but they both go up, but they don't go up. They're not directly proportional. They don't go up by the exact same amount. So you have to be careful there. Excuse me. So for number 5, which of the following is a true statement about a fixed amount of ideal gas at constant pressure? If a sample of gas is heated from 100 degrees Celsius, the volume would increase, and it would increase by a factor of 2, like we just said here, because this isn't in Kelvin. The sample of gas is heated from 0 degrees Celsius to 273 degrees Celsius, the volume will double. So 0 degrees Celsius is 273, and this is double that. So this is double or halving, and because temperature is on the opposite side of the equation to the volume, if this doubles, this will also double. So this is correct. Number 2 is correct. We can go ahead and look at number 3. Sample gas is cooled for 4. So already this isn't by a factor of 2 because it's in Celsius. See, this works in Celsius because it's the correct amount, right? This is 273 Celsius, and if you change it to be in Kelvin, it would be 273 plus 273. And this itself is 273, so it is a factor of 2. This is the only one that is a factor of 2, which already makes it more right, but also it's correct anyway because it's V increasing and T increasing at the same time, which is correct. They're on the other side of the equation, they're directly proportional. And in this one, these ones are both decreasing, so they're both wrong anyway. So we can go ahead and see that number 5, 2 is right. That one's not too hard. That one's just making sure you know your stuff. What volume is occupied by 500 grams of fluorine gas at 5 degrees Celsius at a pressure of 735 torr? So what we can do here is, I'm sure that I could use the PV equals Nrt equation, but it would be a lot easier if I just use the density equation, because what we're trying to find is the density, because we have the grams and this is the liters, and then we know what the molar mass of fluorine gas is, F2, it's about 36 or so, and we know our temperature and our torr, so we can go ahead and put in density equals, what was the equation? It was P, pressure, molar mass, over RT, temperature. So, as we can see, we have all the variables, or, well, we have all the variables except for liters. The only thing we're missing is liters. So, what we want to find is the density, and we use the grams to find the, okay. So, we'll start by putting in the pressure. 735 torr is not in atmospheres. Okay, stop that. So, we need to convert it. First, we need to 35 over 760 torr equals, and we get our atmospheric count of 7.67. Next, we're going to find our molar mass, so we can go ahead. I don't have a periodic table with me, so I can look one up. Here we go. As we can see, fluorine is about 19, so it's actually about 38 for a mole of F2. This is F2. Fluorine gas forms, is a diatomic molecule. So we have a molar mass of 38 grams per mole. And then on the bottom, we have our R, which is a 0.082. I showed how all these units work together. I'm not going to go through all the units. That would be a waste of time. We've already done that. And we have 5 degrees Celsius. 5 plus 273 is 278. That's not too hard. So all we're going to do is plug in our numbers, and we're going to get a density of 0.9671 times 38. And then we divide that by 0.082 times 278. And then we get our density, our grams per liter of 1.6. So if we have G, we have a 1.61 density of grams per liter. That's our grams per liter equals, rather, let's put the equal over here because it's not going to like it if I do that. For equal right there. There we go. Equals 5. So grams per liter would be gram divided by liter. So we have 500 grams divided by X number of liters. So liters X. We don't know how many. We have to find that out. So how we're going to do this is we're going to just do some algebra, and we're going to swap this with this. Okay, so we can go ahead and plug in 1.61 grams per liter right here, and then here we can put in X number of liters. So as we can see, this is 500. So the G is going to cross out here because it's some number of G's over some number of G per something, and the G being on top on both sides. So this is, you could say this is G over 1, and this is G over L. So this is 1 over L. Rather, this is 1 over L, which is just L, but we can cross these both out. And then that L, because it's technically 1 over L, is actually just L. It's just a liter. And then we want to divide this to get our number of liters. Do that, enter. And we get 310, or rather, I guess we round up to 311 because these don't use, well, one of them does, but this isn't close. So 311 liters of gas for 500 grams of fluorine. So as we can see, it's 5, and that is the correct answer. Next, we have number 7. Go ahead and get rid of this. Or let's see, does this... No, this is a different problem. Okay, so in fact, we can probably... yeah, here we go. Yep, this is exactly what we need. So we want to do, this is going to be another temperature, pressure, direct proportionality, or directly related problem. So what we're going to do is we're going to see that we have a temperature 81 degrees Celsius, which we can go ahead and find out how much that is in Kelvin. I don't want to do the addition there because my brain won't work. So that's just, did I do that right? Yeah, I plugged in the numbers right. And then a pressure of 7 atmospheres, that's the correct unit, 7 atmospheres. And it's 354 Kelvin to, I'm going to do that for this one as well, plus 273. We get 649. So we want to see what we multiply the lower temperature to get to higher temperature, because these are directly proportional. The P will follow the T. So as we can see, sample of gas, closed container. It's not getting out. It's not getting in. The volume isn't changing because it's a closed container. It can't get any bigger. So it has to be the T and the P that change. So our T is going up by X amount, and our P will follow in order to balance the equation, but also to follow physical law. So it'd be 649 over 354. And we can find that our atmospheres increase by 1.833333. Probably repeating forever. So we can find our number of new atmospheres by multiplying this by this multiplier. And we get 12.8 atmospheres. So as you can see, that is correct. 12.8 atmospheres. Easy peasy. And now we can do number 8. 0.65 moles of O2, originally at 85 degrees Celsius, is cooled to such that now occupies 8 liters at 40 degrees Celsius with the final exerted by the gas. I believe this is a density problem. Yes, that does seem to be what it is. Let's see if we can find our forward. Oh, we can't go forward. Here, let's see. No, I don't think that's right. Where is it? I'm trying to find my density. So I'd rather not have to do that. Oh, looks like I can't find it. Oh well, we can just get rid of this. Delete. And we can type this out. Density equals P times molar mass divided by RT. Okay, so as we can see, we have our density, because we have the number of moles, which gives us the number of grams. We have our liters, we have our temperature, and we have our molar mass, because it's O2. The only thing we're missing is our pressure. Now, something that might confuse you is we have 0.65 moles at 85 degrees Celsius. And you say, oh no, I don't know how many moles I have at 40 degrees Celsius. It doesn't mention you losing or gaining moles, so it's going to be 0.65 moles at 40 degrees Celsius as well. So it suddenly becomes a lot easier, as you can see. So first, let's find our density, which we don't have yet, which would be 0.65 times. So first we have to find the number of grams of O2 at this literage, which is, it's O2, so it's 32. So it's 20.8. Then we just do 20.8 over 8 liters to find 2.6 grams per liter. That wasn't too hard. So then we gonna, lol. And our density, so we're just gonna put the equation down. I want to put this here. Excel likes to get mad at you. It's really annoying. So our pressure is our final variable, so we're just gonna leave it as P for now. Our molar mass, as we know, is just 32. And we can put grams per mole, but we don't need to put units in because we already know that all the units work out. So that's 32, and then we divide that by R times T. So R in this equation is going to be, once again, 0.082. It's good to remember that. It is very good to remember that, and I suggest you memorize it because it's a better time than any. And then our temperature is, now, it gives us this temperature of 85 degrees Celsius. This is completely useless. We do not care about what temperature it was before. We care about the final pressure, which is at 40 degrees Celsius. It is currently at 40 degrees Celsius. So really, this 85 degrees Celsius doesn't do anything. Just ignore it. It doesn't matter. And 40 plus 273 is pretty simply 313, because 30 and 10 on top. If you want to check my math, you can. Go ahead. And then we're going to balance our equation because we want to find the P, and it is on the wrong side. So first, we're going to multiply both sides of our equation by 0.082. So you can put it down here, 2.6 equals 2.6 times, and we're going to multiply our density by the R value, 0.082, and we're also going to multiply that by 313. Oh, you just love to move around. Stop that. So, and then we're going to divide both sides by 32, and we will get our final pressure of 2.09 atmospheres, which you can see is 2.09 and is the right answer, number 4. That wasn't too hard. It was just a little bit finagling to make sure our brains worked in the right way. Now, let's see what we're doing next. Okay, this is a pretty simple problem. It might seem a little scary because they have all these numbers and times 10, but all it's really saying is how many moles of gas are there. And this is a big number, but really this is just 16.5 liters. And as we know, as I went over at the beginning of the explanation, 16.5, or sorry, at SCP, 1 mole of substance is equal to 22.4 liters. So I don't want to move things because it'll just take me out of the tile. So 16.5 or 22.4. So we have 0.7366 moles of NO2. Now, it wants to know how many molecules are in this sample. If you don't remember, Avogadro's number tells us exactly how many molecules are in any mole of substance. Avogadro's number is 6.022 times 10 to the power of 23. I hope this works in this thing, because it might not. Okay, it worked. Cool. Sometimes the times 10 to the 23 gets messed up, but it looks like it worked in this one case. So as we can see, we still have times 10 to the 23, but instead of 6.02, it has decreased by a factor of about a fourth. It is now 4.43 times 10 to the 23rd. That E is just the exact same thing as times 10 to the, and then it's positive 23. So if we look in here, there's only 2 to the 23. It didn't increase. There's less than a mole, so this is wrong. And as we can see, this matches our number almost exactly. So it's going to be number 5, and as you can see, that is correct. On to number 10. What is the density of nitrogen gas at STP? Okay, so this is a pretty simple one. So all it's really saying is, do you know the liters of gas per mole at STP? So, and can you find the density of stuff? So nitrogen gas is another diatomic molecule as a gas, so it forms N2, which is about 28.02, give or take, grams. Right, 28.02. And then we want grams per liters, as we can see. So we have our grams, and then we divide it by the 22.4 liters, which we've been harping about so often. So as we can see, we get a density of 1.25 grams per liters, which is here. Sorry, it's number 4. And as you can see, that is correct. On to number 11. Ooh. Voice. Analysis of a sample of a gaseous compound shows that it contains 85. Ooh, this one's a fun one. And 14.3 hydrogen by mass. At standard conditions, 112 milliliters of the gaseous compound weighs 0.21 grams. When it says standard condition, what it means is STP, meaning 1 mole will equal 22.4 liters. So this seems a little bit complicated at first, but we can go ahead and figure and pretty easily figure out more or less what the composition will be by doing just 2 things. First, we know what the molar ratio, molar ratio, sure. The ratio of carbon to hydrogen in this substance is going to be because it gave us the mass ratio, and we know what the mass of carbon and hydrogen are. So what we can do is we can just put down carbon is 12, right? And hydrogen is 1. So what would be 12 over 13? It's 92%. So it's not going to be, this is not going to be correct. So if we put a second hydrogen in, and so this might seem really messy, like I'm just doing something dumb, but look, I just found our formula. That's 1 carbon and that's 2 hydrogens. It is going to be in a ratio of 1 carbon to 2 hydrogens. That was pretty easy. So we know that it can't be 1, it can't be 2, it has to be 3, 4, or 5. And in order to find out which of these 3 it is, now they've given us that it's 0.21 grams of 112 milliliters at STP. So 1 mole of whatever this is, 1 mole, will equal 22.4 liters at STP. And we don't know what the molar mass will be, but we can find out. So, I don't remember, how exactly did I do this? Because there's pretty complicated ways to do it. There's also some pretty easy ones, I think. So, okay, so the way, I remember the way I did it. Okay, so, what times 0.112 equals 22.4, right? What do I multiply? So all we have to do is 22.4 divided by 0.112. Multiplier of 200. That's quite a lot. So our molar mass will be 0.21 times, believe it or not, 200. Because this is equal to this. So if this is in ratio with 1 mole of 200, then this will also be. So we found our weight. It's 42. So there's only so many things this could be. So here we can see this weighs 14, right? What is 42 divided by 14? It's 3. So, you know, we can find our answer pretty simply. It's not that hard. It's mostly just logic. It's like if you really like if you want to like really like do a bunch of number crunching and like use all the formulas they gave us, like you can, but it's just not necessary. They gave us STP, they gave us the temperature, they gave us the pressure. You could use this formula to figure it out, but you don't have to, because all it is just logical things. We know what the thing it is. It has to be 3, 4, or 5 because it's 1 to 2. We know how much it weighs because they gave us number of moles, number of grams. We know it weighs 42. This is 14 with only 1 carbon. With 3 carbons and 6 hydrogens, it's 42. That's pretty simple. So you could do it take a really long time to do it, or you could just not and just think about it. You just gotta calm down, slow down, have a nice little thought about it. That one's not too hard. It looks a little bit scary, but it really isn't. Some of the other ones here are maybe a little bit scary, though. Okay, so let's go on to number 12. A sample of gas contains 0.305 grams of carbon, 0.407 grams of oxygen, and so this is about the same sort of problem going on here, and 1.805 grams of chlorine. A different sample of the same gas having a mass of 8.84 grams occupies 2 liters STP. What is the molecular formula for this compound? Okay, so this seems, a little bit scary. What are all these numbers doing? What's going on here? This is really simple. We're doing the exact same thing as we did last time. So we have 0.305 grams of carbon, right? 0.305. So what we're going to do, oh my, it's so annoying. 0.305 divided by, carbon weighs 12 grams. So we have 0.025417. Why are we getting this number? Well, this number is a per gram of carbon. So this is about how many moles of carbon there are. So there's this many moles in this. That doesn't seem very useful, but we want to know how many moles there are of each of these substances, right? So we can use this as a baseline. So next, we'll divide oxygen by, so it's 0.407. 0.407 divided by 16. As we can see, this is almost the same number. These have the exact same number of moles here. So it's a 1 carbon to 1 oxygen to how many chlorine ratio? Let's find out. So chlorine has a weight of 35.45. So all we're going to do is the exact same thing all over again. It's 1.805 divided by 35.45. And as we can see, this is almost exactly double. So what we have here is we have a 1 carbon to 1 oxygen to 2 chlorine ratio. Ooh, that's not a... Here we go. Ooh, I didn't... There we go. Okay, there we go. So as we can see, we've already found our molar ratio, and we haven't even read the entire problem. It's really like... These are not particularly hard problems. These are just slow thinking problems, right? And it says it's different sample of the gas having a mass of 8.84 grams occupies 2. So this gives us the molar mass. All we have to do is find out how many times do we multiply 2 to find 24. 11.2 times. So all we have to do is multiply 8.84 by numbers 11.2. And we get a molar mass of about 99. So now what we can do is we can add these up, this ratio, and it will be a number that we can multiply to get about 99. So if we add 12 plus 16 plus 35.45, we get 63.45. So I believe I have done something wrong. I remember I did this same thing wrong in the oh my, what did we do wrong here? 1 1 1. See, I do this too. I mess up my numbers all the time. I went a little bit fast. I got cocky, and that happens. What is 2 times 35, guys? It's 70. There we go. So, yeah, I went a little bit too fast. I got a little big for my britches, and I messed up. And I did that the first time around. In fact, I did this exact same thing wrong the first time, but that's all right. You just gotta slow down and make sure you do your math right. So always check over your math if something doesn't add up. So it is 98, and we can see that this ratio is the empirical formula. So we get our number 4, and we can see number 4 is correct. So that wasn't too hard. Just gotta make sure we're not going too quickly on some of these problems, or we will mess up. Anyway, on to number 13. Something colored gaseous compound only contain only chlorine, oxygen is density. Okay, so we have ClNO, density of 7.71 grams per liter at 736 degrees Celsius and 2188.8 milligrams hydrogen or mercury. What is the molar? Okay, so this is another density problem. So as we can see, we've gone the density, we've gone the temperature, and we've gone the atmospheric pressure. The only thing we're missing is the molar mass. So we're going to do this the exact same way we did a problem not too long ago. So let's start by just putting our numbers out there and converting them to the proper units. So 7.71 G per L. Ooh, I have my caps lock on. G per L. There we go. And that equals, our equal sign in here. That equals pressure, so 2188. So I do believe that 760 millimeters mercury equals a atmosphere, but I'm not sure, and I do not remember millimeters mercury. Yeah, it's the same thing as torr. I just wanted to make sure and not, mess up and be wrong, because that is annoying. So all we have to do here to get the right number is 2188.8 over 760. And that gives us 2.88 atmospheres. And then here we have our that's 3 letters, of molar mass, which we don't know yet and was what we're looking for. Next we have our R value of 0.082. And we have 36 degrees Celsius. All we have to do is plug this in. 36 plus 273 to find our Kelvin. And we have 309. And then all we're going to do is we're going to balance our equation. These problems are pretty simple. So equals, and we multiply our density times 0.082 times 309. And then we're going to divide that by our atmospheric pressure. So we multiply both sides of the equation by the bottom side of this equation. And now we're going to divide by this on both sides of the equation. So we get 2.88. And that gives us a molar mass of 67.83. Which we can see right here. We didn't get exactly their number, but we were pretty close. And that is more or less all that matters. We see that's the right answer. And on to number 14. This was apparently part 1 of 3. Very exciting. I can't wait to do the other 2 parts. I can't, but that's all right. So this is just, what does Cl weigh? It weighs 35.45. So we have to find 67.83 because there's only one Cl in each one. So this is just saying, so it only has Cl and oxygen. We just have to find out how many oxygen. All we're doing is the same thing we did earlier. We just have to find, oh my, we just have to find what the ratio of one element to another is in a molecule. So we just take away this one chlorine, because it tells us how many there are. There's only one chlorine. How many oxygens are there? Ooh, that's hard. There's 2. So it's 4. That's not too difficult, I hope. And on to the last part of this very, very difficult saga of hard issues and problems. How many moles of this gaseous compound are there in 15? So this isn't even, like, I don't see why this is even in parts. Like, I guess this is trying to confuse you or something. I don't know. But as we know, at STP, there's 22.4 liters. So we just divide it. So there's 0.67 moles of this compound. And it's just 3 is. I guess this is just trying to get you. I don't know. I don't see how it connects to the rest of these. I guess you could like do some really complicated PV equals Nrt density formula, something or other, but you don't need to. That's not necessary, I hope. Okay, now on to number 16. So this is a combined gas law, which she went over, I believe, this last Tuesday was the combined gas law one. The Thursday, so 2 Thursdays ago, was the one where she explained the density and the basis of gas laws. Last Tuesday was when she explained combined gas law and I think something else. And then on Thursday, I think she mostly explained. No, on Tuesday, I think I don't remember. But if you want to go and figure these out more explicitly and better explain, maybe, then do that. But basically, all this is gonna be is we're going to do, so this is a PV equals Nrt problem. Oh my gosh, you are annoying. I know it's terrible. I don't know why you're doing that. This is just a PV equals Nrt problem. So they give us the pressure, yeah, there's pressure. They give us the N, which we have to figure out. They give us the T, we also have to kind of figure out. So this one's not too hard. Let's start by finding our volume. Our volume, they give us in milliliters. Like I said, just put a dot there, 1.988 liters. Not too hard. We don't know what our pressure is. We have to find that out. Just leave it there. And then we have our equal sign here. And then here we are going to have our N. So we need to calculate our N. So the way we calculate our N is, this is a combined gas law equation, like I said. This is actually P total. This is all of the gases combined. And this is in total. This is the moles of all the gases combined. And this is the pressure of all the gases combined. So if we want to find our in total, we just have to add the moles of all the gases up. So what we have to do is find the moles of all the gases. 38 over 32. 32 is O2's molecular weight. So we have 1.81 moles there. And then we have 133 grams of argon gas. Argon gas is, let's go ahead and find out, because I don't remember, 39.95. That's a pretty simple one to put in. 0.95. And we can find that that gives us about 5 moles. We can just go ahead and add those together. Plus, ooh, there we go. That gives us 5.14. That's not too complicated. That's mole. And then we have our R value of 0.082. And finally, we have our temperature, which is just, all we have to do is add 273 to 91. Yep. So now all we have to do is multiply these three together and then divide it by our volume to find our pressure total for these combined gases. So we can go ahead and plug all our numbers in here. That's 5.14 times 0.082 times 364 divided by 1.988. And that will give us an atmospheric pressure of 77.17, which is a lot. And as we can see, it's number 16. That is correct. 77.2 atmospheres. That wasn't too hard, just a little bit of math. Not too scary. Let's see what our next one is. Sample of gas is collected over water at a temperature of 35 degrees Celsius when the barometer is pressure reading that. What is the partial pressure of the dry gas given pH2O equals 42.2 torr? Okay. Oh, I see what this problem is. Okay, so this problem is technically this is a vapor pressure problem. It's just another partial pressures problem. Multiple gases going into P total. So basically what it's saying is that our P total is equal to 688 torr. And our P pressure H2O is equal to 42.2 torr. Oh, these are both in torr. We can go ahead and put that there. And it's asking for it in torr, so we don't actually have to change anything. So we have this in torr, this in torr. We want to know what our P gas is in torr. So P gas, that's not capital P, P gas plus pH2O equals P total. So if we take pH2O away from P total, we will find our P gas. And that's what we're going to do. We're just going to do... Excuse me. Allergies. If we go... My allergies are kind of trying to kill me. They hit on me. So all we're going to do is we're going to do a little subtraction. 688 minus 42.2 torr. I don't know why they made this problem so simple and why they gave us all these other numbers, or just only one other number, but that's all you have to do. And we get our number of 645.8, which we can see is correct. That wasn't too hard. Just have to know that how to do partial pressure. Whew. Man, my allergies are really coming after me today. Oh boy, wow. That is loud. Sorry about that, but I unfortunately have to sneeze. Okay, we're done with that. And then let's see what this one is. A sample of oxygen is collected in a 310 milliliter container over water at 15 degrees Celsius, and the barometer reads 708 torr. What volume would the dry gas occupy at 732 torr and 15 degrees Celsius? Water partial pressure at 15 degrees Celsius is 12.8 torr. Okay, so basically this is a lot like the other problem with some more steps. So first, we know what our torr is at 15 degrees Celsius, and we know that that water pressure, that component of partial pressures, goes away because this is dry gas. There's no longer water in it. So this has no water in it, but this does, and we need to find this without that. So all we're gonna do is just we're gonna take away those 12.8 torr, nice non-flat number that is gonna give us decimal places, which we love decimal places. So, so we have 695.2 torr dry. So this is just P gas. This is not P total. And so what this is saying, so as you can see, we have 300. So this is pressure. This is pressure, and we have here we have it tells us the temperature does not change. As we can see, temperature is the same at all points. The volume though changes. So we have V, and the pressure changes from 695.2 to 732 torr, and the volume starts at we can go ahead and change it real quick. 0.310 liters, and it changes to a number we don't know yet. So what it's asking is what it will change to. I guess it wants it in milliliters, so we might as well do 310 milliliters. Sure. So what we're gonna do here is, as we can see, these are on the same side of the equation. So if this increases by, let's see what amount it increases by. And we could change this to atmospheres, but we don't really need to, because this is internal. This is just within the pressures, right? This will be the same number if we go to unlike with temperature, we're dividing so to get the atmospheres. So it doesn't make any difference. We're not adding or subtracting, in which case we would have to change to atmospheres. But we're not, so we can just do this in this 6.5.2. So this is multiplied by 1.0529. So what we have to do to find our new volume is divide by this. So equals 310 divided by 1.0529. And we get our number 200. So our new volume is 294.42 milliliters. And as we can see, that is correct, 294.4. That wasn't too hard. We just have to make sure we remember that when P goes up, V goes down, especially when N and T stay the same. That wasn't too hard. That was just a simple gas law. There's plenty of them. You don't really need to memorize gas laws. All you have to memorize is P equals N over T. If you understand how the equation works, everything becomes much more simple. So that was number 18. Ooh, we're getting along. We're almost done. Ooh, it's going to be bored. What am I going to do after this? My time. So much time after this. Just kidding. Anyway, let's go into number 19. So we have a 5.2 liter sample of a gas collected over water. So we have to take away the water partial pressure. Again, surprise. The barometer 706 torque. Dry sample of gas at a mass of 5.6 grams. What is the mass of 3 moles of the dry gas? I swear, I've done this problem like 10 times now. People seem to have problems with this problem. So this is just a simple density problem. So we can go ahead and place this density equals Pm over RT. So we first know our density, which is 5.6 grams, equals 5.6 grams over 5.2 liters. So we have a density of 1.076923, which will equal, and what we're trying to find is the molar mass, right? So on the other side of the equation, I'm not going to put an equal sign because I hope that you can understand that this is the other side of the equation. You can just reference this. We have our I can move it over space. There we go. We have the other side of the equation. We have our pressure, which we will find by taking away 706. This is P total. 706 is P total, and we have our pH2O of 22. So to find the P partial, all we have to do is take away 22. And we also have to want to go ahead and divide by 760. See? And we get our atmospheric pressure in atmospheres, of course, of 0.9. And then we have our molarity here, which is what we're looking for. Or sorry, not molarity. Molar mass. Sorry, not molarity. That's a different part of chemistry. And we have our R value of 0.082, and we have finally our temperature of 24. 24 plus 273 is 297 Kelvin. So all we have to do is balance our do some algebra. We multiply this number times this number. This number. And then we multiply that by 297. And then we have to divide it by 0.9. So this over 0.9. This is a little bit sloppy, but that's all right. So we have our molar mass of 29.14. 29.14. There we go. So this is our molar mass, but it's not asking for the molar mass. It's asking for 3 moles. So all we have to do is multiply this by 3. And we get our number 87.4. Now, that wasn't too hard. I went over a little bit quickly, but basically all you have to do, find the P gas by taking away the pressure H2O. Then just plug all your numbers in to the density equation, and then just multiply your molar mass by 3. It's not too hard. Anyone can do it. It just takes a little bit of knowledge, a little bit of mathematics, a little bit of logic, and you'll figure it out. I actually got it wrong the first time because I did not know about the partial pressure of water, which was fun because I had not watched that that lecture yet. that I have now, so I know how to do it. Now let's go ahead and do number 20. If 0.35 mole of CS2 reacts with oxygen completely according to the equation CS2 liquid plus 3O2 gas equals 3O2 gas plus 2 SO2 gas. Wow, so fun. What volume total would the products occupy if they were measured as SCP? So this is just going to be a partial, this isn't even going to be partial pressure, this is going to be partial volume. Partial volume problem or whatever. Basically, all it's saying is, at STP, how many moles are we getting converted to liters? So 0.35 moles, that would give us, so this takes 1 in and puts 3 out. So we have to, what I'm saying here is that this takes 1 mole. This is the invisible 1. We ignore this, doesn't matter because it's consumed, reacts completely. That means there's no oxygen left over. We ignore this, doesn't matter. 1 mole of this goes into 3 moles of this, 3 moles of gas. This is, just ignore the fact that these are different gases. It doesn't matter. Pretend like they're the same gas. 3 moles are produced. If we put 0.35 moles in, we would get 1.05 moles out total of gas. Now, what we have to do is we want to find the number of liters of volume that they would occupy. And all we have to do that is just multiply by 2.4 because we have this in moles. Moles times this. And we can see that wasn't too hard. It's just number 2. Pretty easy. This is just it's just moles to liters, and just do a little bit of math. Some of these are really easy. Really easy. You just gotta think about them for a couple seconds. What volume of HCl gas is produced by? But some people, I guess, aren't good at math, and that's all right. That's why I'm trying to help you out with it. So let's go on to 21. What volume of HCl gas is produced at a reaction of 2.4 liters of H2 gas with 1.5 liters of Cl2 gas? Okay, so first let's balance our equation. So we have H2 plus Cl2 makes 2 moles of HCl gas. So basically what they're asking is how many liters of gas are going to be produced. This is pretty easy, but you have to understand exactly what's going on here. So basically what's going on here. So as you can see, this is not STP, maybe, I don't know. It's at the same TMP. You could like try to convert it and do some like hanky-janky stuff. Don't do that, please. Note that because these are all at the same temperature and pressure, these can stand in as moles. The liter, just pretend it's not liter, pretend this is mole for this problem because it's all at the same temperature and pressure. 1 liter goes in, and 2 liters will come out. It's pretty simple. And it's asking specifically that HCl gas, it's not P total, it's PHCl. So because 1 mole of H2 and 1 mole of Cl2 goes in on each side of the equation, it's going to be limited by whichever is less, which is clearly Cl2. So we're going to have 1.5 mole go in, 2 mole come out. So all we're going to do is just multiply 1.5 times 2. And we're going to get 3 liters out. This problem isn't too hard. You just have to understand that in this problem, liters can act like moles, at least for the reasoning of finding out how much is coming out on the other side. So that one was a little bit confusing, not too complicated. And we're right. That's great. So let's go ahead and do number 22. Okay, so I saw some people confused about what percent yield meant. So all percent yield means is if you put, so let's say we have our equation, chemical 1 changes into chemical 2. It takes 1 mole in, put 1 mole out. I have no idea what this would be. It doesn't matter. Let's say you put 1 mole in, and instead of getting 1 mole out, you get 0.5 moles for whatever reason. Your yield is going to be for 50% because you only got half of it out. That's what percent yield means. whatever you put into one equation, if you don't get 100%, if you don't get the proper amount out the other side, then you're getting only a percent of that yield, which is the percent yield. That's the percentage of it that you're getting. It's not too complicated, but I guess they didn't really explain. I think she did explain it at one point, but I actually don't remember. But it's not too hard. I'll go over how exactly we do it here, because I'm going over it. So this is all STP. We have our moles. Let's go so we see we have liters here. Let's go ahead and convert to liters. So we do 4.51 times 22.4. We have 101 liters that go in. As we can see, CO2 we're finding the percent yield of CO2. That comes out. Or rather, it's the only one we can use to find the percent yield. We have this much going in, this much coming out. It's a 1-to-1 mole ratio. We have 101 liters going in. We have 16 liters coming out. What percentage of 100 is 16? It's 16%. So, one is just give me our answer. This is really a logic problem. I feel it's more of a logic and math problem than it is a chemistry problem. All you really have to do is turn this into liters, and then you realize I put 100 in, I got 16 out, I got a 16% yield. So without knowing how to do it, I suppose it can be pretty confusing, but once you know how to do it, it's pretty simple, I think. I think a lot of these are really just knowing how to do it, which I guess if she didn't explain it well enough for some people to understand, then it can be a problem, but see if I can explain it a little bit better. And finally, let's go to 23. A 6-liter sample of C2H2 at 2 atmospheres and 293 Kelvin is burned in 6 liters of oxygen gas at the same temperature and pressure from a carbon dioxide gas. So as we can see, if we look, ignoring everything else, 2 atmospheres, 293 Kelvin, same temperature and pressure, 2 atmospheres, 293 Kelvin, it's all the same. When everything is the same in this equation, the atmospheres and the pressure, what can we do? So, well, I suppose there's also volume, but this is the volume. And so what you have to understand is that in these problems that have the atmospheres and the Kelvin, so the liters and the in are directly proportional. They work exactly the same. You don't have to act like these are different. Like, you can pretend like this is in. You can pretend that this is the same number of moles. You can pretend this is 6 moles instead of 6 liters because it's at the same atmospheres and pressure the whole way through. Because the atmosphere and pressure don't change, we don't have to do a bunch of complicated math to find the number of moles, because the liters, like, we're getting liters out. There's no point in changing it. So we can just act like this is 6 moles. This is 6 moles, right? So if we act like this is 6 moles, so what it wants to know is if the reaction goes to completion, so all the oxygen or all the C2H4 is consumed because they're not the same going in, what is the final volume of all gas? So this is P total, right? So already, just looking at this, we can see a lot more oxygen goes in, and we have the same amount. So oxygen is going to limit the equation, so all the oxygen will be consumed. We no longer have any more oxygen. And as we can see, 6 went in, so the equation, so we have this happening, the equation happens 2 times, right? This is not a gas, so this does not matter for our P total. So we get 2 of these out, right? Just go ahead, there's nothing there. That means we get 4 liters of CO2. And because this equation happened 2 times, we consumed 2 liters of C2H4. That leaves 4 liters of C2H4 left, and 4 liters of CO2 were produced. 4 plus 4 is 8, so we have 8 liters total. Or, sorry, it's not P total, that's pressure. It's V total, volume total. So this would be number 6. Like I said, this is more of a logic problem. This is more of knowing how to do it and just doing the problem. So I hope you follow along. I can go ahead and show you a little bit more thoroughly here. So if we do, so the equation is going to happen twice, right? So so we have 6 liters of C2H4. We have 6 liters of oxygen. So O2, 3, O2. We have C2H4. And then we're going to do this. And then we're going to do 2H2O. Now, I can put this in the equation, but we don't care about it because it's not in gas. It's not part of our volume total, so we can just ignore this. This doesn't matter. C2O2. These are all gases. So as we can see, it requires more oxygen. So, and specifically, it consumes 3 moles, or right now, 3 liters. So we're going to do this equation 2 times. We get 2 liters out, so we just do 2 times 2 is 4. We get 4 out, and this is consumed completely, so we have 0. But because this equation happened 2 times, because we only consume 1 liter per equation, minus 1, minus 2, 2 times, we have 4 left. We add this all together, we get 8 liters volume total by the time this equation has gone to completion. This is really just a logic thing. It's hard for me to like explain it in depth because it's just logical math logic, which I guess for some people is not quite as simple. So I hope that if you see an equation like this again, with a problem like this again, you can kind of just sort of follow my train of thought, and you should be able to do it pretty easily. Next, we have number 24. A 37.2 gram sample of impure potassium nitrate, KNO3, was heated to complete decomposition according to the equation 2KNO3 solid makes 2KNO2 solid plus O2 gram. Oh, this one's one of the hardest ones. This one, I think this is one of the hardest ones. So I might have to pull up my notes and see how I did this again. A 32. Ooh. Lots of talking. Dry gas produced at 2 liters at 74 degrees Celsius, 77.74%, KNO3, 1.1 grams. Okay, so what we're seeing here, so this is a little bit complicated, but I need y'all to follow along with my train of thought. So we don't get information about this, not really. We get information about this. They're talking about the gas. See, liters? This is not a gas. They're talking about oxygen here. So when we do our density equation, we're doing oxygen gas, right? So we have 2 liters of oxygen gas at 74 degrees Celsius, 777 torr, right? We don't know its density, but we do know its molar mass. The molar mass of O2 is just 32 grams per mole, right? So this is everything we need. These 3 give us everything we need to do the density equation. And then using this liter, we'll find how many grams of oxygen we got from this equation. And then using those grams of oxygen, we can convert that to moles. And we can find out how many moles of KNO3 went into the equation. We can find out how many grams, using this molar mass, were in this sample. And then we'll find the percentage of this sample that was KNO3. That will give us our answer. So this is a little bit of a step. Each step is pretty easy, but you have to keep all your numbers in the right place, right? So let's start by finding our temperature in Kelvin. And then we'll find our atmospheric pressure. Ooh, that's not right. And then this is the right numbers. So if you don't remember our density equation, it's density equals, and then it's going to be our molar mass, 32. Oh, let's put in parentheses. 32 times, and it's PM, so pressure. So it's going to be this number. And then we divide that by our R value, so 0.082, times our temperature, and then enter. And we find our density to be 1.149 grams per liters. So now that we have our grams per liters, so because we have 2 liters, this is this many grams, and this is per 1 liter, right? So this is exactly 1 liter worth of grams. So we have 1.14 grams if we had 1 liter. But if we have 2 liters, we multiply by 2 to find out how many grams we have. So we have 2 liters, so we're going to multiply this by 2. Do this times 2. That's what grams per liters means, is that we have, say we had 10 grams per liters. For every liter of gas, we have 10 grams of whatever molecule it is. So we found how many grams we have. Now what we need to do is we need to find the number of moles to go back through this equation here. So we're going to put this in, and we're going to divide it by the molar mass, which is 32. And we find we have 0.071861 moles. Now, when we see in this equation, 1 mole of oxygen came out, but 2 moles of KNO3 went in. So what we're going to do is we're now going to multiply. See how this is lots of steps. We're now going to multiply this by 2 to find out how many moles of KNO3 went into the equation. And we find we had 0.1437 moles of KNO3 go into the equation. Now we have to turn it back to grams. So we're going to find how many grams there were. So we have our grams per mole, our molar mass, and we have our number of moles times 101.1. And we see that we had 14.53 grams of KNO3 in this impure potassium nitrate sample. So all we have to do is finally, our last equation, we have to divide 14.5 by 37.2. And we can see we had a percentage of 39%. You just have to multiply that by 100 to get the percent. As we can see, it's number 24. That is the right answer, and it rounds up there. And finally, we have number 25, our last problem. This took me way longer than I thought it was going to, but that is all right. Y'all are the ones who have to watch it. Okay, finally, number 25. Consider a diagram shown below of 2 glass bulbs connected through a valve. This is going to be a partial pressures problem, which apparently seems to be rather confusing for some of you, so I will go over it slowly. Okay. So the volume for each gas, A and B, first, let's VA. So our volume for gas A is going to be 48 liters, and our volume for gas B, VB, is going to be 16 liters, right? V total is going to be 64 liters, right? So we get our P total is going to equal 420 torr. So what this is asking us is, if we mix them together, what will the pressure of B be? So, technically speaking, these aren't ideal gases, but we assume they are. So theoretically speaking, this would be, so these are the exact same pressure. So when we mix them together, the pressure is still 420 torr, just like it was in each of them individually. But now that they're mixed together, if we want to know how much pressure is being exerted by B, we have to find, okay, what percentage of the V total is B? It's 1/4, which is 16 over the V total, 64. So our B gas is 1/4 of the liters of gas in the container. So because it's 1/4 of the volume, it's also going to be 1/4 of the pressure. So we just multiply our pressure, our P total, by 0.25 times 420 to get 105 torr of partial pressure for gas B. It's going to be 3. If you don't understand this, I'm not going to lie, I don't 100% understand this as well. I would suggest going back to when she explained partial pressures and rewatching that section of the notes, or maybe asking one of the teachers. But that was the entire the entire homework number 10. I hope that what I said and did helped and that you were able to complete it in a timely manner. And that took me 1 hour and 30 minutes. Holy crap, that was really long. Alright, I will see you later. Until next time. Ooh, infinity, fun.